Hello, once again, AP Calculus students. Mr. Record here from Avon High School, and we're going to be looking at section 4.4 in the Larson textbook, which talks about something that sounds kind of important, the Fundamental Theorem of Calculus. We're here with my fourth period class. Hello, all right, they're excited, as you can tell. So this is a very long section, and it turns out we're just going to talk about one small piece of it today, and that's this first idea right here. Oops, as I said, this first idea right here. The first fundamental theorem of calculus. And you're going to be exposed to this in a multitude of ways over the remainder of your calculus lives. And it's going to also play a pretty big role on the AP calculus exam. And it's highly likely, if you're watching this video, that you probably have been exposed to this before if you've talked about area under a curve and have done some work with some Riemann sums, which is pretty much the way that most calculus classes are organized. So what exactly is the first fundamental theorem of calculus? Well, it says here that if you've got a function f of x that's continuous on a closed interval ab, and if we declare that capital F of x is the antiderivative of f of x on that closed interval, then here you go. It says the definite integral of f of x with these boundaries, A and B, right? Again, probably not a new thing for most of you. Seeing these boundaries is just going to produce a slightly different interpretation of our answer to our antiderivative. You would go ahead and integrate the function f of x as normal, and we call that capital of f of x. But then you're going to end up taking these boundaries and one at a time, very systematically, you're going to plug them in for any x value in that answer. Do the same with the lower boundary, a, and the all-important piece to remember is that there is a subtraction sign in between. And it's that subtraction sign that can often cause some problems because subtractions tend to kind of do things like that. So in a nutshell, that's what the first fundamental theorem of calculus does. And we'll address one more time what it actually means here in just a moment. So on the next slide here, I've got three fairly simple examples of how to apply this idea of the fundamental theorem of calculus. So let's tackle 1a first. So we're going to take the definite integral of x squared minus 3 from boundaries 1 to 2. And you've heard me say the word definite integral. Obviously, we see it in the directions. A definite integral, one more time, is just an integration expression that has the boundaries, as opposed to an indefinite integral that will not have the boundaries. So if we take the antiderivative of x squared, hopefully you can remember from a previous lesson that you would have x cubed over 3. And then if we take the antiderivative of 3, of course, with respect to x, we would have 3x. Now, you're probably wanting to put a plus c at this point, but I want us to hold off on that. You're going to find out that the c's are going to end up disappearing regardless, so it's just better if we don't even introduce it to this problem to begin with. So if we wrap all of this stuff in parentheses and then put our little vertical bar, some textbooks, some teachers might put the vertical bar with some like feet, and by feet I mean these little dashes. Whether you do that or not, it's completely up to you, but it's still going to be understood if you write that little bar without the feet. What this is basically saying is that we're going to evaluate this such that x is going to be 2 and x is going to be 1, and we know innately that we're going to subtract those because of the fundamental theorem. All right, so the rest of this is pretty much like algebraic arithmetic. So if you go ahead and plug the 2 in for the x, you would get 8/3 minus 6. And like I said, this is the part where students can really run into the biggest trouble. We know that there's a minus sign, but by plugging in 1 into a pair of these expressions, 1 cubed over 3 is 1/3, and of course 3 times 1 is 3, we know that this is going to be wrong because we're going to want to subtract this entire quantity. So I'm going to advise all of you to put parentheses around that every time. every time. And the reason is because this sign is always going to be a subtraction. That's never going to change. Okay? Now, you can just use some grouping techniques because of these rather ugly kind of things that you have to add and subtract. So if I deal with just the 8/3 minus the 1/3, you can see that we're going to have 7/3. And then if we kind of focus on the rest of this, -6 or -6, subtracting a -3 is really -6 plus 3, which would give us -3. And then when we take a look at this, 7/3 minus 9/3 as a common denominator, we can see that that's going to give us -2/3. And lo and behold, you have your answer. All right, now depending on what you have seen prior to this particular example, some of you may have been in a course like my students where we did investigate solving integrals like this, but do you remember us having to use the limit process? You guys loved the limit process, didn't you? You probably would like to do the limit process on this problem to check the answer, am I right? No, okay, good, I'm wrong. You don't want any part of the limit process anymore. You know, the limit process was wonderful in that it did yield an exact answer, but it took quite a bit of time and effort. Now, you've also dealt with problems like this where you use what's called a Riemann sum, where you would use an approximation technique, whether it was a left endpoint, right endpoint, midpoint, trapezoid. The problem with those methods is that they were approximations. All of that is now a thing of the past. We have an exact answer, and just to make sure that this is still meaning the same thing that it meant before, I'm going to show you a little calculator way to check this. You guys don't have to follow along here with me, but if I just enter this particular expression, I believe it was x squared, right? X squared minus 3. So it's just a pretty standard parabola, right? And then I'm going to use a menu option that I don't think we've ever done before here in class. We're going to analyze this graph, but we're going to choose finally option 7, integral. So when we click on that, we see a question being posed before us, lower bound, and we have the ability to kind of slide this bar back and forth, which is very common when you do a lot of analyzed graph features on the TI Inspire. Well, we want to find the area you know, between the curve and the x-axis between 1 and 2, if you recall, right? The problem is that, you know, if you try to slide this and get this like right at 1, you could either guess at it, which is kind of like what's happening right now, or if you kind of move the little cursor up on the x-axis, and by the time it says point on, and you're in the sort of general neighborhood of 1, chances are you're probably okay. But I don't even like to rely on that. I think the easiest way is just to type in that lower bound from scratch. Bam, I typed in a 1. When I hit enter, it's going to lock that in. For a minute there, I thought I typed in -1, but I'm okay. And your upper bound is there at 1. And if I move this over to the other side, you can see now the question becomes lower bound. It's kind of interesting. You could screw up and actually put the upper bound in first, I suppose, and you'd still have a way to like fix yourself. But we're going to go ahead and move this to the right. And now the question says, what is the upper bound? And I'll type in 2. And then, does this answer look familiar? That is our -2/3. Okay, and for my particular students that are watching this live, can you see that there is just a little bit of area right here that is above the x-axis that's positive, and a greater portion of area that's negative below the x-axis, but the net result of those two areas does produce this -2/3. Okay, and then don't forget that you always have your good friend, the scratch pad calculator page, that you could also do the same thing by the shortcut Shift plus, integrate from 1 to 2, and you could type in the function, but I believe that I probably don't have to type the function in since it's already in the entry line of the graphing page, and that's also going to give you your -2/3 without a decimal. All right, so everyone's convinced that definite integration is still area. That's not changed. What's changed is the way that we're going to go about finding it, and we're going to use our skills of integrating now, which is much more convenient. All right, let's take a look at these other two examples. Probably won't do the calculator work with them now that you're all convinced, but we can practice this definite integration technique nonetheless. So if we're taking the antiderivative of 3 square root of x and evaluating it from 1 to 4, we might first of all think of this square root of x. If he was having a dream, he would be thinking of being written as 3 to the 1/2, right? So we would have 3 times x to the 3/2 divided by 2/3, right? And then we would evaluate all of this from an upper limit of 4 down to a lower limit of 1. Now, I think it would be in our best interest to do some simplifying, right? Oh, I got some dirty looks from my students. Now I know why. Thanks. I kind of made a mistake here. I want 3/2 here, don't I? I'm so used to, just like many of you guys are probably used to, multiplying by the reciprocal all in one step, but I went ahead and kept this still in the denominator, so it should still be 3/2. But yeah, you're right. Just in a moment, he's going to flip upside down and become 2/3. All right. So sorry if we had any confusion there. We're going to have a 2 out in front, right? 3's are going to cancel. And then x to the 3/2 probably would be okay if we kept it written like that, but we can also convert this back into radical form, and I think you guys might have a little bit more luck in trying to evaluate it like that, but you guys can do either way. Now, I see that there is a 2 common to what's going to end up being a pair of terms when I plug in 4 and 1, so my personal preference would be to take any constant out in front and just basically factor it. And now you can run your 4 in, and you can either take the square root of 4 and cube it, or you could take 4 cubed and square root that. All right, either way, square root of 4 is 2, cubed, you're going to get 8, just like the square root of 64 would be 8. And then obviously if we run 1 inside of our x position, we're just going to get a 1. So you can see 2 times 7 is the result, or 14. And once again, if we were to sketch this particular curve, we would find that it would have an area of 14 under the curve and above the x-axis between 1 and 4. Okay. Our last problem here, a little trig example. And if you're still in a position where you look at the integration of secant squared and you're not quite 100% sure of what it is, or you find yourself having to look back in your notes or whatever, that's probably a pretty good indicator that you want to spend some time with some formulas. Flashcards, you can try to use Quizlet, you can do a variety of things, but you want to get to a point where you look at the integration of secant squared and immediately you know the answer is tangent, right? Did a lot of you already remember that, hopefully, from last week? And then your boundaries were going to be pi over 4 to 0 here. Don't really have to put this in parentheses because it's a monomial, but it's never a bad idea to do that. Okay. Now, one thing I haven't been doing before, I'm going to do that here, is just to kind of reiterate the fact that what's going on is that we're going to plug in our two boundaries separated by a subtraction. All right. It's just that here we have some trig ratios to attend to. The tangent of pi over 4, that's the tangent of 45 degrees, right? A 45-degree angle is going to have an opposite side and an adjacent side that are in the ratio of 1, right? And of course, the tangent of 0 is going to be 0. So despite the fact that this problem was trigonometric in nature, it really wasn't any more difficult to solve. So definite integration can apply to those guys as well. All right, so anyway, you've got 3 nice examples there of definite integration and basically the beginnings of the first fundamental theorem of calculus. In later videos, we'll expand upon this idea. We'll talk about the second fundamental theorem of calculus, and then more recently, we'll even talk about the average value of a function, which plays a very prominent role on the AP exam. Anyway, I hope this helps, and we'll see you next time.